All right, here's your homework from last time. We were talking about like the accumulation of change and what it was like underneath the graph. So if we have a tank filling up with water at a constant rate of 4 gallons per minute, we don't have to worry about taking the intervals because the rate's the same. So when we talked about Alice growing, she did not grow at a constant rate. When Alice was growing, her rate of change in between the different intervals wasn't consistent. So Alice's graph looked something like this, and when we were looking at her rate of change, it was great. If they tell us it's a constant rate of change, then no matter how many minutes are involved, then when I'm looking at that tank filling up, I don't have to take pieces of it. So that constant rate of change that looks like this, I can go ahead and take each of those areas by multiplying length times width, looking at the intervals, and it doesn't change. My area underneath that doesn't change, so that's fine. One of the biggest things for you to understand is if we're talking about it's filling up at a rate of 4 gallons per minute, along our y-axis is our rate. So if that happens to be 4 gallons per minute, and no matter how many minutes it's going at, 1 minute, 2 minutes, 3 minutes, 4 minutes, because this rate is the same, I can say I've got 1 gallon, 2 gallons, 3 gallons. Well, that's not true. Like 1 times 4, which is 4 gallons, 2 times 4, which this represents 8 gallons because I've added on another 4 gallons. At 3 minutes, this represents another 4 gallons. Each one of these intervals is constant. That's 4 gallons. So when I look at it over 2 minutes, that's 8 gallons. 10 minutes, 40 gallons. So it doesn't ever change. There's a constant rate of water coming into my tank. So important you understand that we're looking at the graph of the rate. If you want to know the part of your test that you screwed up on the most is understanding whether you're looking at the graph of position, velocity, or acceleration. Are you looking at the original graph of the function? Are you looking at the derivative, the rate, or are you looking at the acceleration, the second derivative? That we're looking at the graph of the rate. The rate is 4 gallons per minute. Each minute, 4 gallons add to my tank. It's constant. All right, so then when we sketch it according to time, there we have this understanding, and no matter what, our tank is filling up without a problem. When we get down here to our number 2, that tank is being filled with water, but my rate is not constant. So when I look at how much it's filling up at a rate of 0.125 at this instantaneous, at this time, so I can say, okay, that gives me that many gallons. When I look at my second minute, my rate is now at 8 gallons per minute. You're like, oh, snap, somebody must have turned it up. Because now all of a sudden the water's coming in at a whole lot faster. But it wasn't this rate back at this time. It was not 8 gallons per minute at this time. So I have to do some math and I have to kind of approximate. So this time is in between a half a minute and 2 minutes. So I'm going to go ahead and say it was 8 gallons this whole time. It kind of wasn't. So what we're going to talk about today is the tighter our intervals get, the more accurate our data. Because somewhere between half a minute and 2 minutes, it was 1 gallon per minute, 2 gallons per minute, 3 gallons per minute, 4 gallons per as the rate increased. But as far as all I know is at this moment, this was the rate, and that's the best I can do. So during this time, which was 1.5 minutes that were in between there, I had an 8 gallon per minute rate. And think about that again, distance equals rate times time. And I put my distance into quotes because it's the amount of water in it is rate times time, the distance I travel is rate times time. That rate times time is going to give you that ultimate value that you're looking for, 12 gallons. So total now I have this many gallons in my tank. Now between 2 and 10 minutes, what the heck? Now I'm going at 1,000 gallons per minute. So during this 8 minutes, my rate that my water was flowing into the tank seriously shot up. It went from 8 to 9 to 10 to 11 to 100 to 200, 300, 400, 999, 1,000. So that's the best I can do is assuming now, obviously I think it's an overestimate because during this time in between, it wasn't 1,000 gallons per minute the whole time, but that's the best I can do. Talk to your group mates, please, about the difference between problem 1 and problem 2. Go. All right, so let's look at the other side. Let's look at the other side of the homework. Now again, we're looking at the rate. This graph shows my derivative. So when my derivative is negative, my function's decreasing. When my derivative is positive, my function's increasing. So I guess Miss Holdaway likes hot dogs, I don't know. So the graph below shows the rate at which hot dogs are on Miss Holdaway's plate. Assume she starts with 10 hot dogs. It's a lot of hot dogs. At 0 minutes. So where is the number of hot dogs increasing? And where is the number of hot dogs decreasing? So here, where the derivative is positive, the number of hot dogs is increasing. Here, where the derivative is negative, the number of hot dogs is decreasing. I'm thinking about she's cooking on the grill at a barbecue, and she's got 10 ready to go. And the people come and be like, oh, I'd like a hot dog, please. And they take hot dogs. And then she cooks the next batch and adds them to them. Let's picture that scenario. That makes sense to me. All right. So how many hot dogs are on her plate after 6 minutes? When I did this the first time, I didn't read the question. So pardon my, I was just adding up how many hot dogs she lost. So this is 4 hot dogs. And this is 2 hot dogs. If you haven't figured it out, the area of a triangle is 1/2 base times height. So ultimately 6 hot dogs were taken off of the plate while she was barbecuing. I stopped. I didn't read the 6 minutes, so when I did my math, I kept going. I said, okay, this is half of a hot dog. This is a whole hot dog. These are all whole hot dogs. And this semicircle, I don't know if they got like some toddler eating hot dogs in circles or pies with hot dogs. I don't know. Maybe a puppy came and took half. I don't know. Took a piece. I don't know why we're measuring hot dogs on pie, but go with it. So here's her half a hot dog, and then 1, 2, 3, 4, 5 hot dogs are here. And then here is my semicircle pi r squared. So if you want to know what formulas I'm expecting you to have at your front of your brain, area of triangle and area of circle, I think are fair game, in addition to area squares and rectangles. So I was all ready to say this many hot dogs were put back on her plate, and then I was like, oh snap, it was 6 minutes. So she had 10, lost 4, last 2, put a half a hot dog on, and then 1 more. So she had 5.5 hot dogs on her plate after 6 minutes. At the end of her time grilling, she's got 9.5 plus 2 pie hot dogs. I don't know whose hot dogs are in the shapes of circles, but okie dokie. All right, so when we're talking here, the graph below shows the rate of change. Again, it's the rate of change. Do you notice every single time, like I've gotten screwed up on whether I'm talking about position or the derivative or the second derivative. So every time I read one of these questions, I circle what it is that I'm talking about to make sure my head is straight. So the graph below shows the rate of change. Here it's increasing, here it's decreasing, here there's 0 rate of change. The graph below shows rate of change in number of people in the movie theater. Assume no one was in the theater at 0 hours. So 160 people at that first minute are in the theater. On what interval is the number of people in the theater increasing or decreasing? If it's increasing, my derivative is positive. This is where the number of people is increasing. Now, we know it's increasing at a decreasing rate. Here it's increasing at a constant rate. Here it's increasing at a decreasing rate. Here it's not changing. And then from 5 to 10 hours, it's decreasing. How many people are in the theater after 5 hours? This area under the curve helps us determine the total amount of people. So this one shot here is 160 people. This triangle here is 1/2 base times height, which is another 160 people. No, and nothing changes. Nothing changes here. So I have 320 people in my theater when I add these two together. Are you okay with that? Yes? Okay. So nobody comes or goes. There's no change here. Okay? Now what we're talking about here is when people start to leave. So this is people per hour, this is hours. So when I multiply these units together, people per hour times hour, my hours cancel out, and what ends up happening underneath my curve represents people. If it's below the x-axis, it's negative. People are going home. People are leaving. So after 10 hours, I lose 1/2 base times height here. These 80 people leave. And then 1, 2, 3 times 40, 80. So 3 times negative 80, 240 people leave. I think I forgot to finish answering this one. So I lose 320 people, right? Which means nobody's left. Do you buy that? Isn't this 320? Yeah. So here's my 80 people leaving. Here's my 320 people left. Therefore, no people. Are we okay with that? All right. Turn to your partners and explain to them how this graph shows people. Turn and talk. How does it show people? All right, so today we're going to use something called Riemann sums, and we're going to repeat that process.
Can we go back to the homework for just 1 second?
Sure.
A number.
We use the rate of Alice's growth at different times represented by the black curve. I highlighted it in pink to determine how much Alice grew. We multiplied her rate by the different time intervals, which we represented with the rectangles shown. So if you look at each of my different rectangles, here I have a rectangle that represents her height after 2 minutes, and here I have a rectangle that represents her growth after a little over 3 minutes. So do me a favor, with your group mates, talk about what our x and our y-axis represents, and talk about these questions. Go ahead. So my x-axis is my time in seconds, and my y-axis is her rate of growth. She's not growing at all. She's growing a little bit. She's growing more. She's growing more. She's growing more. So her rate of growth is increasing. The area under that curve, what does it represent? What does it represent? If we're talking about feet per second, and we do an area calculation of length times width, what is feet per second times second? Yeah, it's Alice's height. Because what we're looking at, if her rate is feet per second, and we're multiplying it by her seconds, notice what we're left with unit-wise is Alice's feet. So we're looking at her total height. So we do the best we can with estimating. Anytime we're dealing with a curve, coming up with water flowing into a tank that doesn't ever change, that's easy. It's a constant rate if it's this straight line. But if it's a curve, getting that area under the curve, the best we can do is estimate. So do you think that these rectangles give us that good answer? Do you think it's close? Do you think it's an overestimate, an underestimate? Talk to me about what you think. Yeah, I would say we're missing out on this part here, this itsy bitsy part, right? But here, when we calculate this area, this part undercounts, but that part over is over. When we estimate this area, this part undercounts, but that part's over. The only one that we're pretty good with is if you look at this area that I'm going to put in yellow, we're only over that little much. This is all stuff that counts. So if I want to talk about how much space is under this curve, everything above the curve is going to be an overestimate. So is it a perfect answer? Is it a perfect thing? No, it's an estimate. In fact, it's going to be an overestimate. Now here's the thing. I can totally increase my accuracy if I draw skinnier rectangles. If I drew one big rectangle, that would seriously be an overestimate, wouldn't it? Because the only thing underneath would count. So as I break it up into smaller and smaller estimates, that's what we're going to start thinking about today. Okay, here's this guy named Bernard Riemann. And it's focusing on his face. What do I do if I can't perfectly find the area under the curve? He was the one that came up with just use rectangles to approximate the area and get as close as you can. Keep in mind, he's back doing this. I always like to just kind of put these dates in context. He's doing that before we had electricity, before we had indoor plumbing, before we had cars, before we had, he's busy worrying about area under the curve. And all this stuff is happening. And you kind of want to say to him, thanks for all your time and efforts, Bernard. But I'm sure people would have appreciated modern plumbing. I don't know. All right. So we're going to explore this concept using this website that's kind of super cool. And we'll see if we can get it to work for us. So it's these Riemann sums, and what ends up happening is I can put a function in here, and I can change what A and B and C represent. So just work with me here. If I have A is going to represent where I'm measuring from interval-wise. So if I set A at 1, I'm just talking about the area under the curve. Trying to figure out how to get it to zoom out a little bit. There you go. My area under this curve between A and then B represents the end of my interval. I can go up to 10, So if I talk about the area under the curve from 0 to 10, I can take this all the way back to 0. Sound okay? All right, so N is going to represent how many little triangles or how many little rectangles I draw. Notice the more rectangles I draw, the more accurate I'm able to get that area and the less I have. So if I continue to draw rectangle after rectangle after rectangle after rectangle, notice I'm pretty dead on with my area. If I go all the way back, the lowest it lets me do, there's one rectangle. How accurate is that? Right? And then I can continue drawing rectangles. P represents a different concept because I'll slide P back and forth. Here is this P, and I want you to see what the difference is between this P and what happens to my boxes as I slide. What do you think P represents? Where does P, what do you think P represents as I slide back and forth? Just watch one rectangle. Everybody pick one rectangle. Focus in on it like this. What happens to that rectangle? I want you to now look at where is that rectangle hitting my curve. Ready? Everybody look at where your rectangle at the top is hitting the curve. Everybody focusing on their rectangle? Tell your partner which one you're looking at. Are you watching? Where's your rectangle hitting the curve? So here's the deal. I'm going to look at this rectangle here, and I'm going to say this rectangle is hitting my curve right here. And I'm going to say that if I were to figure out this area under the curve, I would calculate this area and add it to this area, and so on and so on. Everybody okay with that? Once I slide P, what happens to my area calculation? What P represents is whether we're drawing the rectangle to the left of the curve or to the right of where it hits the curve. Because what ends up happening as my P comes back here, this rectangle is drawn here, and as I shift it, this rectangle, instead of hitting here, it's this corner that hits up here. So it's an interesting conversation. Stretching or question? Oh, stretching. So what's interesting is we can see that as I increase my number of intervals, I get more and more and more accurate. As I decrease my number of intervals, I lose my accuracy. Where was I? Like here? Was I at like 10? What we're going to play with today is what kind of calculation we do. We're going to talk about having the right hand of your box touch the curve. We're going to talk about having the left hand of your box touch the curve. We're going to talk about having the curve split your boxes. And then there's a fourth method called the trapezoid one, but we decided not to go with that one. Sound okay? So we're going to come back and visit this, and I'll be sure to put this website so you can play with it. but it's neat to see. The big idea here is for you to see that the more ends I have, the more accurate my curve is. And that end represents my number of intervals, that number of boxes that I end up drawing. All right, so let's talk about Sweet Bernard. So we're going to say this curve represents the rate of Alice's growth as she eats a different kind of cake. Based on our discussion last class, what does the width of each rectangle represent? What is our width? Well, thank you. And we'll call it an interval. So we'll go back, and the interesting thing is when we come back here, Alice's growth rate wasn't a sine function. It was more of a, hold on. Alice's growth rate, where's my graph? Shoot. Equals 2 to the x. Thank you. 2, I thought I hit that. Okay, we like that better. Okay. Alice's growth rate was more of an exponential conversation. So if you look at our ability to calculate her height, if we look at increasing our ends, see how it gets closer and closer to the curve? If we measure from the left, this is kind of what we did. All of our boxes were overestimates, weren't they? If we measure from the right, we end up doing what kind of estimate? End up doing a little bit of an underestimate. If we measure from the middle, maybe that's a little bit more accurate, right? Okay. So we'll go back here again. What does the width of each rectangle represent? A specific interval in time. What does the length of each rectangle represent? Her rate of growth. All right, answer me this. What does the area, when I find area equals length times width, if you prefer to think of it as distance equals rate times time, what does that area represent? Her total height, right? Her total change in height. So go ahead and give yourself some conversations. Our interval of time is measured in seconds. Her rate of growth is feet per second. And her height is going to be measured in feet. That area is going to represent, and don't forget, we're going to talk about her accumulation of how much she has grown, her accumulation of her height. So if you want to go back and think about the hot dogs, how many total hot dogs? The accumulation of hot dogs, the accumulation of people, depending on whatever that rate was. All right, let's check out the back. So the sliders on the graph, when we play with the applet, how does each slider affect the graph? So we're just going to do this fast. I'm going to post the applet so you can log onto your computers and play with it. But I want you to recognize that A is the start of your interval, B is the end of the interval, N equals the number of rectangles that you use, and P is going to represent where the rectangle connects with the graph. So P equals 1, it connects on the left. P equals 0, it connects on the right. When P equals 0.5, that's when it's the center or the midpoint. Our big idea here is if you add up on the areas of the rectangle, what you're going to get is the total area under the curve. So take a look at number 4. What do you notice about the combined area of the rectangles when n is small and when n is big? So I'm going to come back over here and I'm going to show you again. If I have n being super big, what do you notice? If I have n being super small, what do you notice? All right. These are about using Riemann sums to approximate the area under the curve. So here we have a graph of 4x minus 1/2 x squared, and we want to use the Riemann sums to find the approximation of the total accumulation of change on this interval. And what we want to do is we want to divide that area into equal sub-intervals. So I know so far some of the examples we've had unequal sub-intervals, but we want to make it so n is going to be the same size. When we talk about how many rectangles we're using, we want to use the same ones. Okay, so first of all, we know it's an upside down quadratic, so we're not surprised to see like this. Riemann sums to find the approximation total. So what we need to do is figure out how much space exists, because our interval is going to be from 2 to 8. So this is my A and this is my B. So the first thing that I'm going to do is subtract B minus A to give me how many total sections of the graph I have. What is the distance between that I'm measuring my area? And then what I'm going to do is, because they told me to use 3 sub-intervals, I'm going to go ahead and divide that by my n. So this n is going to represent how many little rectangles I used. So that means that each triangle is going to have each rectangle is going to have a width of 2. Does that make sense? Yeah? So when I'm talking about my interval of 2 to 8, I'm just talking about approximating this area here. So 2 to 8 is what I'm going to do for each one. So when I do this, there's a difference between whether I'm calculating it according to a left-hand sum or a right-hand sum. And my left and right, remember, left is the one that makes the L, your right is the other one. That's going to be the side that touches the curve. So when I go to look at each of these intervals, I'm going to look at drawing a box where I have a width of 2. That's my width of 2, because I'm going to have 3 different sums. And then what I'm going to do is I have to draw a rectangle, and I'm stuck with drawing that rectangle wherever it hits the curve on the left. My next place where it hits the curve is here. So my next rectangle is going to exist here. And my next rectangle hits the curve here. So when I'm going to estimate this area under the curve, I'm going to find the area of these three rectangles and add them together. Because here's my three subintervals. So for my subinterval number 1, my area is equal to my width, which is 2, and my height, which is 6. For my second rectangle, my area is going to be my width, which is 2, and my height, which is 8. My third rectangle, my width is 2, and my height again is 6. So I know my total area is going to be 40. If I have a right Riemann sum, what I'm going to do right then is look at each interval, and instead of measuring where it touches on the left, I'm going to pay attention to where it touches on the right. So my first rectangle is going to be like this. My second rectangle and my third rectangle, I don't get to even draw. So when I go to find my area under the curve, this is the math that I'm doing. I have my rectangle 1 and 2. So if I go to find my area of rectangle number 1, my area equals my interval, which is 2, times my height, which is 8. My area number 2 of box number 2 is going to be my width, which is 2, times my height, which is 6. For my third interval, my width is 2, but my height is 0. Notice we have a significant discrepancy. Discrepancy in our values. And I'll take you back to thinking about the website. Our third choice for looking at where the box sets is if we centered the box over. So a left-hand sum, it touches the graph on the left hand of the box. For a right-hand sum, it touches the graph on the right-hand side. That go like this. And it's interesting, on that last example, we couldn't really say whether it was an estimate that was over or under because it was a curve and it changed. But if I had a straight line and I was doing my Riemann sums, if I have a left-hand sum and I was drawing my boxes that were attached to the left hand, would you say on average that this was an over or an underestimate if my function is increasing? Yeah. It's an underestimate. If I have a right-hand sum where my rectangles, why do I keep saying triangles? Because of all my geometry. If I have a right-hand sum for an increasing area of the function, would you say that that is an over or an underestimate? Talk to your partners about the decreasing function and whether a left hand or a right hand is over or under. Go. So what you'll notice that's kind of interesting is depending on whether your graph is increasing or decreasing, whether your left hand or right hand sum over or underestimates it, changes. So what we need you to do is get kind of used to thinking about whether you're doing a left hand or a right hand, depending on where it's touching the graph. That's what becomes that most important part. Our right hand touches on the right. All right. So let's just talk about this example. If we don't have a graph, we can figure out left hand and right hand sums if we have a table of values. So the rate at which water is being pumped into a tank, I don't know why we're obsessed with putting water into tanks, but it's the same with flagpoles and geometry. Like we're always measuring how tall is the flagpole? Who cares? The rate at which the water is being pumped into a tank is given by the continuous and increasing function r of t. The table of selected values of r of t for the time interval 0 to 12 minutes is given below. So if we want to find the right-hand sum with 4 sub-intervals, so what we can talk about is how our intervals work. So if we have 4 sub-intervals, from 0 to 3 is 1 sub-interval. From 3 to 6 is 1. From 6 to 9 is another. From 9 to 12 is another. And they all have a change in time of 3. And I want you to picture that as the width of your rectangle. Are you okay with that? Yeah? Say yes.
Yes.
Okay. So when we start talking about our total interval, is from 0 to 12, what we want to do then is take 12 minus 0, and if we wanted 4 sub-intervals, that's how we get that width of our rectangle, which is going to be 3. You okay with that? Now notice it's not going to always be the same. Here we have 2 sub-intervals, and we're going to have a conversation about which was the most accurate. Does that make sense? Okay. So if I'm doing a right-hand sum, I'm going to care about the right-hand part of each interval. From an output stance of 7 gallons per minute to 13 gallons per minute, I want the 13. So my first calculation is going to be this rate of 3 times this 13, which is going to be my first height. And that's going to give me a total of 39. gallons. When I look at my second interval, I have my width of my rectangle times a height of 18. And what does that equal? 54? During my next right hand, I have 3 times 23, 69. And then my last interval, I have 3 times 27, 71. Yeah? I don't trust my brain.
Why did we skip 7?
Because I'm doing a right hand sum. So I want you to picture the boxes. If I have an interval, like see here where if I have an interval, I'm going to go with this right hand value. That's the height of this right hand end of the interval.
So, I still don't get why we wouldn't use the first one, 7.
Because this is the left hand. See how that's the value on the left?
Gotcha, okay, sorry.
Okay, that's okay, keep asking. All right, so then when I add up all these values together, yeah?
3 times 27 is, isn't it
81. Thank you. It is a Smartie. Go, Catherine. Oops, why didn't it like that? Oh, 2 pluses, that's why. So I have 243 gallons when I calculate it with my right hand sums. So here's the deal. I used my right hand sums because I was looking at where the rectangle hits the graph on the right. Okay. If we talk about where the graph hits it on the left, notice I still have my same data, but if I have 2 sub-intervals, so if my total interval is from 0 to 12, my change in my interval is going to still be 12, but then instead of dividing it by 4, I'm going to divide it by 2, which means my intervals are now going to have a width of 6. So instead of just going to the next guy, I got to go to have an interval of 6. So I'm just going to have 2 intervals. And because I'm doing a left-hand sum, for each of my intervals, I'm just using the value on the... So I'm going to have a width of 6 and an output of 7. A width of 6 and an output of 18. I'm not trusting my brain. So then when I tally them, and notice that's all I have. So now I have 108 plus 42. I have 150 gallons inside my tank. Okay. So when we look at each of these guys, is the approximation greater or less than the true value? Because my tank, because it's an increasing graph, if I do a right-hand sum of an increasing graph, it ends up to be an overestimate. If I do a left-hand sum of an increasing graph, it's an underestimate, and this estimate here is pretty lousy anyway, because guess what? I only did 2 intervals instead of 4. It'd be interesting if you calculated it using the left-hand sum. with the 4 sub-intervals. And you can do that. 7 times 3 plus 3, 13 times 3 plus 18 times 3 plus 23 times 3. Okay. So that's it for left-hand, right-hand sums. It's on video. By this time, your data chart, which was due a while ago, if you need to rewrite it, feel free. Make sure that it has the title, the labels, the units, etc. Neatness does count. Your explanation of your trip has to be in paragraph form. I took a trip too, like with capital letters and punctuation and real spelling and all that fun. The graph of your data needs to be where you converted your time and your speed units to feet per second so that you're talking about same conversations. Your graph of your data should have had a title, labels, units, and your x-axis in 15-second intervals, and a smooth curve connecting those data points. That was what was expected of you, and it's listed on the back of your assignment sheet when I gave you this. Okay. So now I've made you 3 copies of your graph for the next part of the project. Here's the thing, if you're unhappy with your graph and you're like, I didn't do it right, I want to start over, fine. You figure out how to get 3 copies of it. Go to Kinko's, go to wherever has a copy machine. Because you're going to use one of each of those graphs for the following. You're going to use a left-hand sum, you're going to use a right-hand sum. Next class, we're going to talk about the midpoint sums. I'm pretty sure you can figure out what that is. That's where P is equal to 1/2 and your rectangle splits your graph. We made your intervals 30 seconds, not 15, so that otherwise you'd be doing 40 calculations. Does that make sense? Instead you're now doing 20. Now, you can do your calculations on a separate sheet of paper if you want to do it electronically and you want to turn it in. That's fine. These final questions need to be answered. If you want, I gave you this so that you could calculate it as you went. Your left-hand sums, you need 20 calculations. Your right-hand sums, you need 20 calculations. We'll talk more next class about the midpoint sums. 20 calculations. What's on the back are your 3 thought questions. So whatever form your project is turned into me includes either this piece of paper with all of the data in addition to your graph and your graph's 4 copies original and your 3 sets of sums, your explanation, and your data chart. So the project is due this day when I see you. Next week, next Thursday. This is when the project's due. If you don't turn the project into me, then that's yours to finish over spring break. I'm not giving you homework over spring break. If you don't get that project due, I will still accept it when I see you on the 12th without a late penalty. It's a 4th quarter conversation. What questions do you have? Okay, so